Introduction to the geometry of space-time and gravity. Arthur Eddington's 1919 eclipse expedition confirmed that light is deflected by massive objects like the Sun. Newton's law of universal gravitation states that any two masses attract each other through gravity. When light passes a massive object, the path may appear shorter or longer, but all photons arrive at the same time. The challenge with special relativity. Special relativity holds that the speed of light is constant, but light paths near massive objects raise questions. For example, if photons take different paths, say from A to B and from C to D, they must still travel at the same speed to arrive simultaneously. Einstein's solution. Time flows differently depending on the gravitational field, addressing the paradox. Effect of gravity on spacetime. Gravitational time dilation. Time slows down closer to massive objects. For example, Bob at the top of the Himalayas ages faster than Alice at the bottom of the Mariana Trench. Experimental confirmation. Atomic clocks on airplanes show that time runs faster at higher altitudes. Visualizing time dilation with a spacetime cylinder. Spacetime diagrams represent how objects move through time. When rolled into a cylinder, stationary objects circle the cylinder, while moving objects spiral down it. Massive objects affect the flow of time, slowing it near the object's gravitational field. The cone model of spacetime and gravity. Introducing Earth into the model. Spacetime flares into a cone with time running slower at the wider base, which is closer to the object. Two objects, for example, ants at different altitudes, experience different time intervals, with time passing slower at lower altitudes. Curved spacetime and the cause of gravity. The curved geometry of spacetime causes objects to naturally follow curved paths and fall toward massive bodies. Stationary objects appear to fall because their straight-line paths bend toward the wider end of the cone. Gravity emerges as a result of space-time curvature, slowing time and guiding objects toward massive bodies. Gravity and the speed of falling objects. Objects that start falling from rest initially move only through time. As the object falls, more of its motion shifts from the time dimension to the space dimension, increasing its speed. If the height were infinite, for example, an infinitely tall Eiffel Tower, the falling object would eventually reach the speed of light. Conclusion. Curved spacetime as the root of gravity. The slower passage of time in strong gravitational fields causes objects to follow curved paths, resulting in gravity. Curved spacetime governs both the flow of time and the motion of falling objects, making it the underlying cause of gravity.